So, hello guys, and this is gonna be like a very quick and dirty tutorial kind of video. So basically, what I'm gonna be covering here is how to make native like Python perform sufficiently fast compared to like Numpy and stuff like that. So basically, the trick here is most of the time you can get away with this. There are some exceptions, like when you're using objects and stuff like that, where this wouldn't work as well. But for most numerical calculations, this works. And this is basically just to use Numba. To get numbers, just pip install Numba. So let's take this example here. We have matrix multiplication. So for this first one, I'm calling it native. The only thing not native about this is that A, B, and C are NumPy arrays, but it wouldn't be even remotely useful with lists, because lists are inherently slow and they are technically Python objects where this would break down. But anyway, what I'm mostly referring to as Pythonic here, as native, are all these like nested loops, which in Python, for loops are also inherently somewhat slow most of the time. So this is where we'll see the benefits of this kind of thing. Basically, when you have loops with numerical calculations. So this is basically our example. It will be a matrix multiplication. And here, the first thing that we have is basically the same exact example. The only difference that we add is just this one line here, the decorator, at numba.jit. That's all. And for the second one, it's the same, but we use njit instead of jit. N, it's basically the same thing, but the n here sort of tells Numba to, like, we're using NumPy here, so get all you know from NumPy and try to optimize even further on top of when you use JIT. Now, the second two examples we have here are the same, JIT and njit, but this time with no-GIL. The no-GIL allows us to use p-range instead of range, which is basically, in the context of a for loop, it basically allows the for loop to be cast in parallel and to be computed on different cores to make it even faster. This is very beneficial for something like matrix multiplication. And yes, same thing here for njit. Now, we will be multiplying the same array with itself basically here, just as an example. And also we'll be comparing it to the native NumPy matmul, which will be faster, but as you'll see, compared to the native, all of these are just way better. So let's run this. The first one will obviously take a bit of time. And by the way, here we are gonna print the execution time. There. So as you can see, for a 300 by 300 matrix, the native one took almost 16 seconds. And then with just one decorator, it dropped down to 0.2, 0.3 seconds, which is a hell of a big improvement. With njit, it almost halved it. Then with the parallel jit, it's almost the same as njit, and even with the parallel njit, because NumPy inherently also does a lot of parallelism. But here, as we can see, with the native NumPy, the time wasn't big enough to even register. So yeah, native NumPy is much faster. And also, a good thing to point out here is the first time you run the script, all the Numba ones will be much slower. But then, because it compiles them it's kind of like a greedy compilation. So if you don't use the function, it doesn't compile it. But then once you compile it once, it's really, really fast. So for the sake of example, let us put this to say 400. Maybe we can get a number out of the NumPy maximal in terms of time taken. But yeah, that's basically it. And also, a good thing to note here, if you have a powerful, well, decently powerful NVIDIA GPU, Numba also has the CUDA jet, which you could use to make the process even faster. There we go. We got a very small number for the Numpy one, which is, I mean, it's impressive as it is. The native one almost doubled in time. The other ones remained fairly consistent. And what's even more interesting, the parallel JIT is slower than the parallel NJIT is slower than the normal NJIT, which means that you could maybe be opening threads more than it's necessary, so it's actually like the time to open that thread, it's reducing performance. And also, for those who do not really care about numerical accuracy, there's also this argument, fast math. If you set this to true, and let's do it on the parallel, and let's do it on all of them, actually. Now we'll see like a bit slower compilation. Let's take this down to say 200. So okay, now it's even faster. Wait, what am I saying? Of course it's faster. Let's take this back up. Actually, let's run it to see like the first compilation how slower it is maybe. Yeah, it's about the same. Okay, let's take it back up to say 300. So we could compare with our first one. Our first one was 2.5 and 0.25 I mean, and 0.16. So now let's see. Oh, there we go. Yeah, it's a bit faster. Well, not by very much, but I mean, it's there. This is mostly used for like fast accumulation and fast division, because I believe, don't quote me on this, but I believe it uses, there's like that C division, which doesn't handle for errors like the Python division does, so you could just skip over that. But don't quote me on that, I'm not entirely sure if that's how it works. But anyway, so that's basically like a quick and dirty way to make math in Python faster. Basically, you just import Numba, and then decorate your functions with @numbajit or @numbanjit. Pretty straightforward, and it also sort of keeps you true to the native Python kind of workflow, whereas with other like optimization tricks like Python, you would need to like go to C and work with that and deal with whatever C makes you deal with, which it's not, I mean, I personally prefer that because I have more control, but I get that it's not for everyone to play with, and most people would be like, it wouldn't be very attractive to them to use C and deal with the C errors. Those are like, they're not really helpful. But yeah, anyway, that's the whole point of the video. I hope you liked it. I hope you can make use of Numba to speed up your code and make it a bit more efficient, because Python needs quite some help in that regard. So yeah, until next time, see you. Bye bye.